Okay, so let's start. In the last class, we were looking at some basic tail bounds on random variables, right? So I introduced three probabilistic inequalities. One was Markov's inequality, which says that if x is a non-negative random variable with a finite mean, then the probability that x is greater than or equal to some delta for any delta greater than 0 is upper bounded by the mean divided by delta, right? And while this is not useful in itself, it can be used to derive a bunch of better inequalities. The first one that we saw was Chebyshev's inequality, which says that if x is a random variable with finite mean mu and finite variance sigma square, then the probability that x minus mu deviates by an amount of delta is upper bounded by sigma square by delta square. Now, immediately you see when we go from Markov's inequality to Chebyshev's inequality, we go from a 1 by delta bound to a 1 by delta square bound. Right? For delta large enough, obviously this is a better bound than Markov's inequality. Right? But the only problem is that you need to know some more information, which is the variance. So if you have a higher moment, then you can get a better bound. In fact, you can go on improving this to first moment, second moment, third moment, and so on. But then if you know all of the moments, or in other words, you know the moment generating function, then in fact, in many cases, you can obtain an exponential tail bound. So, and really that's the class of bounds that we will be most interested in, and the class of bounds that we'll study for much of this course. So the Chernoff bound says the following: if we have a random variable x for which the moment generating function exists, at least it should exist for some values of t. Even if it's not defined for all t, it's still okay, as we'll see later. But then for any t for which the moment generating function exists, the probability that x minus mu deviates by an amount delta can be upper bounded by the moment generating function divided by e raised to t times mu plus delta, where you can choose any t for which the moment generating function is well defined. All right, and you can get sort of both a bound on the right tail as well as the left tail, except with some minor variations in the bound. But ultimately, all of it depends on the moment generating function and e raised to t times either delta plus mu or delta minus mu.
Sir, in Markov's inequality,
Yes.
mean equal to 0, that implies that probability less than or equal to.
Well, if the mean is equal to 0, then what can you say about the random variable? Remember, it is non-negative.
The probability of x equal to 0 is 0.
Exactly. So then you don't need a bound at all, right? So the problem is interesting only when the mean is strictly greater than 0. Any other questions? All right. So let's see what happens to the Chernoff bound when instead of x you're interested in a function of random variables, in particular our favorite quantity, which is the average of n IID random variables. Right. So the quantity that we're interested in is Sn, which is 1 over n summation I equal to 1 to n of xi, and we'll assume that all the xi's are IID and the expected value of xi is equal to mu. So in this case, what is the probability that the average Sn minus mu is greater than or equal to delta? In fact, let's look at the simpler case where I'm only interested in the right tail. right? Again, if I just apply the Chernoff bound, then I get that this is less than or equal to, or let me write it in a slightly different way first. So this is my Sn. I can write this as probability that 1 over n summation I equal to 1 to n xi minus mu is greater than or equal to delta, which is the probability that summation I equal to 1 to n. So instead of getting a bound on the average of these n random variables, it's the same as deriving a bound on the sum of the random variables. N times mu is greater than or equal to n times delta, right? It's the same thing. I've just sort of manipulated, or it's just simple algebra, right? Now, if I use the Chernoff bound, what do I get? Yes? Correct. And what is the random variable? Summation xi, right? So let's maybe do it slowly. If I call this y, if I call this mu prime, and this quantity delta prime, what do I get? This is phi y of t, just to make sure that we keep track of what random variable we're considering, divided by e raised to t times mu prime plus delta prime. All right, and if I just plug in for y, mu prime and delta prime, I get phi summation over I xi of t divided by e raised to mu prime is n times mu and delta prime is n times delta, so nt into delta plus mu, right? But what is phi of, what is the moment generating function of the sum of IID random variables? Sorry, careful. Sum. Okay, what is phi of summation I xi of t? Remember, it is expectation of e raised to t times summation I equal to 1 to n xi. Yeah, so this is just expectation of a product I equal to 1 to n e raised to t times xi, right? But we know that xi's are all independent of each other, right? So what is expectation of a product of independent random variables? It's the product of expectations. So this is just product I equal to 1 to n expected value of e to the t times xi. E to the power xi, if x1 and x2 are independent, what can you say about f of x1 and f of x2? How do you define independent random variables?
If we have two random variables, pairwise should be independent property of
Fine.
X,
Okay.
probability.
Okay.
So if the function is ready, then they are
If the function is
the function of random variable which we are considering is the
correct.
exponent.
Okay.
Because of the property of exponent, they are
No, I'm saying that any function, you take any function, they're still independent. So a necessary and sufficient condition for independence is that for any events, let's say E1, E through up to En, probability x1 is in E1, E2, xn is in En, right? This is equal to the product of the events, right? The random variables are independent if each of these events are also independent, and this happens for every single E1, E2, E3 up to En, right?
whatever they
Yeah, for whatever for every E1 through En, if this happens, if this is equal to product I equal to 1 to n, probability xi is in ei for all E1 up to En, then they're independent. Right? Okay, let me take any transformation of the random variables. So probability, let's say f of x1 belongs to let me call it E1 prime, x2 belongs to E2 prime, and so on. All right, this is some quantity. This is equal to the probability if f of x1 is in E1 prime. It happens if and only if x1 lies in some other E1 double prime, which is f inverse of E1 prime. No. So irrespective of what the function is, whether it's invertible or not, what do I mean by f inverse of E? It means the set of all points which are mapped to E. Yeah, so f so f is what? It's a mapping from R to, let's say, R, right? What is f inverse of some set A? It is the set of all x in R such that f of x is in A, right? This is well defined. Even if f is not an invertible function, it need not be 1-to-1, it need not be on to, doesn't matter, right? This quantity is still well defined. So this probability so this probability is equal to this probability. F inverse of E1 prime and so on, right? But I know that x1, x2, x3 are all independent. So for every E1 prime, E2 prime, E3 prime, this is equal to the product I equal to 1 to n, probability that f of xi is in F inverse of E1 prime, which is the same as the product I equal to 1 to n probability that f of xi lies in ei prime. So this holds for every function, as long as the function is operated on each individual random variable. So if, let's say, x1, x2, x1 and x2 are random variables, may be independent, and I take two different functions of both x1 and x2, for example, f of x1, x2 and g of x1, x2, these may not be independent of each other. Yeah.
So, with the same property holds for uncorrelated methods.
If they're independent, they are uncorrelated.
If they are not independent and uncorrelated.
Okay.
Then if x and x are uncorrelated and not independent,
okay,
will the function of those random variables, again the same f of x1, g of x2,
okay,
will there be uncorrelated?
try it yourself.
It's not.
Can you give an example, a simple example?
Prove it actually using the problem.
Sure. Yeah. So they won't be uncorrelated. This is a property purely of independence, right? Because I could go again. This had to hold for every single E1, E2, E3 up to En. So functions of uncorrelated random variables are in general not uncorrelated. Functions of independent random variables are independent. Okay, any other questions? So, nice exercise. Find x1, x2 such that expectation of x1, x2 equal to expectation x1, expectation x2, but this does not hold for f of x1, f of x2. Find two random variables x1, x2 such that x1 and x2 are uncorrelated but not independent, but f of x1 and f of x2 are not uncorrelated. Okay, so coming back to what we are looking at, the moment generating function. Okay, so we saw that the MGF of a sum of independent random variables is simply the product of the moment generating functions of the individual random variable. Now they're also identically distributed. So expectation of e to the power txi is e to the power expectation of e to the power tx1, right? Equal to 1 to n expectation of e to the power tx1, which is just phi x1 of t whole to the power n, right? Okay, so what does that give us as the Chernoff bound? So the probability that Sn minus mu is greater than or equal to delta is upper bounded by phi x1 of t divided by e raised to t times mu plus delta whole to the power n. Right? And this is sort of the bound that we were looking for. If you recall from our previous class, after we derived the Chernoff bound, we also tried to derive the Chernoff bound for this average, right? And we saw that the bound that we get, when we dealt with Chebyshev's inequality, we were also interested in finding out the probability that Sn deviates from the mean by a certain amount. And using Chebyshev's inequality, we were only able to get 1 over n upper bound on the probability of that this deviation is greater than or equal to delta, right? But now from a 1 over n bound, we now got an exponential in n bound, right? So in fact, what this says is that for at least most random variables of interest, at least if you have a sum of IID random variables, then the probability that the average deviates from the mean by an amount delta, in fact, decays not just polynomially in n, but in fact exponentially in n. We'll take a few examples. We'll go back to the example of the Bernoulli random variables and see what this is equal to. Okay, so for the Bernoulli random variable, what is the moment generating function equal to? So this is expectation of e to the t times x. What values does x take? 0 or 1? Okay, so what do you get? Okay. Okay, so what is this equal to? Okay, I mean it's just a, so what is the final value equal to? Yeah? Just what about when x is equal to 0?
Oh, yeah, +1.
Correct. So it's just equal to p into e to the power t. So this is when x is equal to 1 plus 1 minus p into e to the power 0, which is just 1. Right? Any questions? Okay. Fine. This is some particular quantity. For any t greater than or equal to 0, I have this particular. In fact, for any t, this holds. Right? Now, what happens if I just plug this into the Chernoff bound? Probability that Sn minus p, the mean is equal to p, is greater than or equal to delta is less than or equal to px of t divided by e raised to t plus mu, which is t plus p whole raised to n. Right? Which is just px of t is p times e to the power t plus 1 minus p divided by e to the power t plus, I'm sorry, I missed something. Oh, it should not be e times e to the power t times p plus delta. Whole to the power n, right? Okay, so now if I'm able to find one particular t for which the quantity over here is less than 1, then it's enough to show that this decays exponentially, right? And that's something in fact you can do. And in fact you can prove a much stronger upper bound simply by choosing the t carefully enough and simplifying. You can show that the probability that Sn minus p is greater than or equal to delta is in fact less than or equal to e raised to minus n times p delta square divided by 2 plus delta. Right? And this holds for any delta greater than or equal to 0. Delta greater than 0.
What's the value of P?
You have to be careful. So in fact, this is a homework problem for you. You can, I think, I don't remember which question it is in the homework, third or fourth problem. And for delta between 0 and 1, you can improve this a little bit. I mean, this is slightly nicer to work with. Minus n times p delta square divided by 3. Just so that there's just one term which involves delta. So this is a homework problem. In fact, in your homework, you're asked to find the mean variance and the moment generating function of a number of random variables which we will use frequently in this course. Any questions? Okay, so let's do one more example. Let's see what kind of Chernoff bounds we can derive for the Gaussian distribution. Right. Again, I'm assuming that X is Gaussian with mean, say, mu and variance sigma square. What is the moment generating function? This is another homework problem. So the moment generating function also behaves in some sense the same way. So the PDF is e raised to minus x minus mu the whole square by 2 sigma square. whereas the moment generating function is e raised to sigma square t square by 2 plus mu times t. So it is e raised to some quadratic. Okay, so this is, so then the probability that x minus mu is greater than or equal to some particular delta is less than or equal to e raised to t times mu plus delta. Which is e raised to minus t times mu plus delta plus t times mu plus sigma square t square divided by 2. T times mu cancels. So it's just e raised to minus t times delta plus sigma square t square divided by 2. Alright, so this is fine. Now this is true for every t, right? So I can choose the best possible t, which gives me the best possible upper bound. How would I do that? Yeah? Okay, minimize it. How do I minimize this particular function? Okay, so basically you try to minimize the exponent. So the minimum of this is equal to e raised to minimum of the exponent, and the exponent is a quadratic function. What kind of a function is this? Is it convex, concave, neither? Convex. Is it convex or concave or sorry? It's concave for all t greater than 0. For all t greater than 0, it is concave. Right? In fact, even if t equal to 0, then you just get a constant function which is still concave. So this is concave for all t. How do you verify whether a function is convex or concave? Yeah? Take the second derivative, and in this case, what is the second derivative equal to? Sigma square. So the second derivative of the exponent, that is minus t delta plus sigma square t square by 2. This is concave. So minus t delta plus sigma square t square by 2 is concave for all t, and you can get that from the second derivative test. Any questions? So if it's a concave function, then you know that by taking the first derivative and setting that to 0, you get the maximum value. Yeah, sorry. I'm sorry, my bad, I'm looking at the wrong thing. So this is convex. E raised to negative of this is concave. Right, so this is convex. So if I take the first derivative and set it equal to 0, then I get the minimum value. Sigma square t square. So what is the when is the minimum achieved? What is, yeah, it's equal to delta by sigma square. And what is the minimum value of the exponent? Yeah, so what happens when I substitute t equal to delta by sigma square minus delta square divided by 2 sigma square? And this looks very similar to the PDF itself, right? What is the form of the PDF? It is e raised to x minus mu the whole square by 2 sigma square times some particular constant. And what the Chernoff bound tells us is that the right tail, the probability that x is greater than or equal to, or x minus mu is greater than or equal to delta, is at most e raised to minus delta square, which is basically my x minus mu the whole square divided by 2 sigma square, right? So this is my mu, this is x. What I want is this is my delta. So this is my mu plus delta. And I want the probability that I want this particular probability, right? Now, what is the value of the PDF at this particular point? At this particular point, what is the value? X is equal to mu plus delta, right? Yeah. I'm sorry, what is the value of the PDF at this particular point? This is fx of mu plus delta. And what is fx of mu plus delta? Yeah. So it's 1 by 2 pi sigma square e raised to minus delta square divided by 2 sigma square. Right. So that's a very nice feature of the Gaussian. The tail of the Gaussian is in fact proportional to the value of the PDF at that particular point. Sorry, what probability?
From 0 to mu plus.
Correct.
Property is 0.67.
So this is some delta, right? Delta is not dependent on sigma. Delta is something which is independently chosen. Any questions so far? So in this case, the Gaussian, as well as in the previous case, the Bernoulli, we derived bounds in which the probability of the deviation was behaved roughly like e to the minus delta square times some constant. So in this case, if you choose, let's say, n equal to 1, then you get e raised to minus p delta square divided by 2 plus delta. And in this case, the case of the Gaussian, this probability is e raised to minus delta square divided by 2 sigma square. This is not something that you will see for all random variables. These classes of random variables are rather special in the property that the tail is exponentially decaying. So as you increase delta, the probability that x is greater than mu plus delta decays exponentially in delta. In fact, it decays exponentially in delta square. And this is a particularly nice phenomena that is helpful in some cases, and such random variables are called sub-Gaussian random variables because they behave like Gaussians. So in these cases, so in these examples, the probability that x minus mu is greater than or equal to delta, we saw that this is less than or equal to e raised to minus some constant times delta square. So random variables which satisfy this are what are called sub-Gaussian random variables. And we'll study sub-Gaussian random variables in more detail as we go along.
By default,
Gaussian random variables are sub-Gaussian by definition. In fact, that's why these are called sub-Gaussian random variables, because they have tails that behave like Gaussians. So we just, again, this is not the tightest bound, but we saw the example of the Bernoulli random variable, right? In which case, again, I said that so I have e raised to minus n times, or e raised to minus some constant times delta square.
Is it generally in probability they will say when n tends to infinity for binomial random behaves differently?
Sure.
Is it because of the sub-Gaussian?
We'll explore this in more detail as we go along. But again, the phenomena that you're attributing to is that if you take a scaled average of random variables, then that converges in distribution to a Gaussian by the central limit theorem. But that's a different phenomenon, right? But we'll see more examples of sub-Gaussian random variables. And at this point, I'd like to only say that this does not happen for all kinds of random variables. For certain kinds of random variables, this decays exponentially in delta. These are what are sometimes called sub-gamma or sub-exponential. And again, this you can guess where this comes from. If you take an exponential distribution and find the tail probability, then that just happens to be e to the minus some constant times delta. Yes, an exponential distribution is sub gamma or sub exponential. The gamma distribution in general is sub gamma or sub exponential, but these are not sub-Gaussian. So every sub-Gaussian distribution is sub gamma because they have faster decaying tails. We'll I mean what I'm not given you an exact definition yet because all of these are just bounds, but you can characterize each of these using their moment generating functions. Okay. The main point is that for sub-Gaussian distributions, you can have tails that decay as e to the minus some constant times delta square. For sub-exponential distributions, we have tails that decay exponentially in delta. And for many other random variables, you have neither of these behavior. It does not decay exponentially in delta. Something much weaker. All right. And in fact, for all random variables with finite variance, we know that it decays at least polynomially in delta. Why? Chebyshev, right? So it's definitely C by whatever sigma square divided by delta square by Chebyshev for all random variables with of course finite variance. Right? So this is fairly general, but this is what we would like to happen. Okay. Any questions? Okay, so before we move on and explore these different classes of random variables, let's see some applications used based on what we've seen already. All right, so let's first right. So let's see an example of random graphs. Right? So we'd use this to just study, basically just study some basic properties of random graphs. So there are different ways of generating graphs at random. So you need to specify a distribution on graphs. The simplest model is the so-called Erdős-Renyi model. And I'll denote this distribution G of n comma p. So this consists of graphs which have exactly n vertices. And what is p? Basically, it tells you what is the probability that two vertices are connected by an edge. Right? And the model is extremely simple. You take n vertices. For every pair of vertices, you connect them with an edge with probability p. With probability 1 minus p, they are not connected. For they're connected by an edge, single edge. So this consists of n vertices. For every ij pair of vertices, I comma j is an edge with probability p. So with probability 1 minus p, I comma j is not an edge. And this is done independently for all pairs. So if you take sort of a simple case where I have just 3 vertices, what are all the possible graphs that I can get using the Erdos-Reddy model? Yeah, so this is one particular configuration where there's no edge between any pair of vertices. The graph could have one edge. How many configurations are there? There are 3 of them. Two of them could be connected. And how many configurations do I have? Again, I have 3. So here, I mean, loosely speaking, I'm assuming that each of these vertices is labeled in some particular form. So for example, these 3 are distinct graphs. And then all of them could be connected. So remember, I'm just picking a graph at random. So what is the probability that this graph gets chosen?
1 minus p whole cube.
1 minus p the whole cube, right? So there should be no edge between these two, and that happens with probability 1 minus p. No edge between these two, that happens with probability 1 minus p. Same 1 minus p. So the probability that this graph gets picked is 1 minus p the whole cube. What is the probability that this graph gets picked? All right. Okay. In particular, what is the probability of this particular graph being picked? P into 1 minus p the whole square. So each of these has probability p into 1 minus p the whole square. And each of these, what is the probability of occurrence? P square into 1 minus p. And what is the probability that this gets picked? P cube. All right. Great. So now that we are fairly comfortable with the model itself, let's see what other properties these classes of graphs have. Right? What is the expected number of edges? In general, for in G of n comma p, yeah. P times n choose to y.
Like there are total of n choose to possible edges.
Correct.
And each edge can be each other the probability of p.
Correct. So basically, what is the expected number of edges equal to? You can write this in the following way. So in general, how do you count the number of edges? You can look at all possible pairs, I comma j, and then see if there's an edge between them or not. So although it's fairly simple, I'll sort of try to do it in a kind of formal sort of manner because that will help us. So I can write this as summation over all possible pairs, I comma j, so again, this is some notation which you will sometimes see in the literature. So if I have a set, n choose 2 is just the set of all pairs of elements from 1, 2, 3 up to n. Right? And the number of such pairs is exactly n choose 2. I'm sorry?
Expectations.
We'll get to that in just a minute. Okay. So this is all possible pairs of what? So again, some more notation. So I'll write a 1 with a subscript right. So this is what I call an indicator random variable. So it's a random variable. It's basically a Bernoulli random variable, right? It's equal to 1 if this event occurs, that is I comma j is an edge, and it's equal to 0 if I comma j is not an edge. By linearity of expectation, this is just summation I comma j n choose 2 of expectation of this indicator random variable. And what is this expectation equal to? P. Right? So I can take the P outside and I just get a 1. How many terms am I summing over? Whatever. 3 choose, n choose 2 in general. Right? So that is just equal to n choose 2 times P. So the expectation is just equal to P times n choose 2.
Can be modeled as a part of binomial random.
The number of edges is indeed a binomial random. Yes. Sure. You can do that also. Okay. But maybe what we are interested in a bit more is the degree distribution of the edges. Sorry, the degree distribution of the vertices of this particular graph. So let me call di to be the degree. Okay, it's a random variable. So let me perhaps use capital Di. Vertex I in the graph. Right, so this is a random variable. Okay, so it's basically the number of edges which are incident on that particular vertex. Now, the edges themselves are all independent of each other, right? Because of the way we have defined. But what can you say about the degree of two different vertices? Let me take vertex 1 and vertex 2. What can you say about the degree of vertex 1 and degree of vertex 2? Are they independent of each other?
The degree of vertex 1 and vertex 2 is the summation of both of them.
Exactly. So I can say, so in fact, let's go use that particular notation that we had earlier. So I can say that this is equal to a summation over all j in 1, 2, 3 up to n except I. So I run through all of the integers up except I of indicator I comma j is an edge.
Second part you asked, right, the degree of vertex I and j.
Okay.
Oh,
So So here I'm summing over all possible j, right? So let's take 1 comma 2 are d1 and d2 independent. I've defined the random variable, right? I'm sorry. Okay. Yeah. Now I can hear you.
I was saying intuitively it's not because we go for three
Correct.
and if we know that the degree of one vertex is 2,
Yes.
then we know that the degree of the other vertex is not 2.
Exactly. Yes. But can you argue that just by looking at this expression? So if I look at d1 and d2, each di can be expressed as a sum of, in fact, independent random variables. So each of these, so this is a random variable, right? Which basically says whether I comma j is an edge or not. So it's a sum of Bernoulli random variables. If I look at d1 and d2, are there any common random variables in between those two? Yeah, the edge between 1 and 2, right? So in fact the answer is no, because both contain one comma 2 is in E is common. And in fact, you were, as you rightly pointed out, if you just take the case where the degree of 1 d1 is n minus 1, you know that the degree of 2 has to be at least 1. Right? So they cannot be independent.
Every single word is down. DI and DJ.
Exactly. So in fact, you take any pair I comma j, di and dj are not independent. So there's no doubt about that. But in some sense, they're almost independent because there's only one random variable which is common. And we'll see how that helps. Right? So why am I bringing this up? What I want to know is what is the degree distribution. So if I take, what is the expected degree of vertex I? Yeah? It is? It's n minus 1 into p, right? I'm just summing n minus 1 Bernoulli p random variables. So it is just n minus 1 times p. Okay? Very good. And so now I know that it is n minus 1 into p. So the question is, are all the degrees going to be very close to n minus 1 into p? Okay, so let's just look at degree I. All right, what is the probability that the degree of the ith vertex is not too different from n minus 1 into p? Let's say delta times n minus 1 into p. Yes. Assume that this delta is like very, very small, okay, much smaller than 1. Yeah, we can just use Chernoff bound for Bernoulli random variables because it's just a sum of Bernoulli random variables. So this is 2 times e raised to minus. I can apply Chebyshev's inequality, but I'm only going to get a weaker bound. I want the tightest bound that I can get. Sorry? You use Chebyshev's inequality if you're not able to use Chernoff bound, which is true in many cases, because it's only a small, so you need to know a lot about the random variable if you need to be able to apply Chernoff's bound. As I said, if you want to use Chernoff bound, it means that you know the entire moment generating function. If you don't know, then you can't use it. Or you know some properties of the moment generating function. Chebyshev's inequality, you just need to know the variance. Okay, so I have this. Right? So the question is, how small can I make delta such that the right hand side still vanishes as n tends to infinity? And I am interested in knowing this for different values of p. All right. So suppose that p into, or suppose that p is at least some constant, sufficiently large constant, times log n by n minus 1. Then what is expectation of di? Or what can you say about the expectation of the expected degree of the ith vertex? Right, it's at least c log n. Okay, so this says that probability that the degree minus n minus 1 times p is greater than delta times c log n is at most 2 times e raised to minus, I'm sorry, it should be a delta square c log n divided by 3. Right, any questions? Okay, so what is e raised to, let me write this out a little differently. This is equal to 2 times e raised to log n whole to the power minus delta square c divided by 3. Yeah.
How exactly do you get the right hand side?
You mean here? Which one? You mean this particular quantity? It's a homework, right? So, okay. So, let me take a step back. So, each di is a sum of Bernoulli random variables, IID Bernoulli random variables. And for IID Bernoulli random variables, I have this particular problem, which is a homework problem. That's all that I've used so far, right? So, this is a sum of Bernoulli random variables. Sorry, this is an average, right? I just multiply by the number of Bernoulli random variables. Right? This is the same as saying probability that summation I equal to 1 to n xi minus n times p is greater than or equal to n times delta. It's okay. Any other questions? Is it clear how I got this particular bound? Great. So what is e raised to log n? Assuming that the log is to base e. It's just n. 2 times n to the minus delta square c divided by 3. If delta is some constant which is independent of n, then it means that this decay is polynomially. Right? Is it clear? Okay, great. But this is only for one of the degrees. Right? What is the probability that all of the degrees are very close to n minus 1 times p? That is, all of them are close, or all of them are roughly the same. So the quantity that I'm interested in is, or the probability that I'm interested in is, what is the probability that di minus n minus 1 times p, the expected value, is less than or equal to delta times c times log n for all I, or it's the same as looking at the probability that di minus n minus 1 times p is greater than or equal to delta times c times log n for at least 1I, because this event is simply the complement of this particular event. Straight. Right? So 1 minus this is equal to this particular quantity.
What will be for all the probability?
I'm sorry?
The probability of this one.
Correct.
What do you mean by for all every individual should be?
So basically for every single vertex has degree which is very close to n minus 1 times p. It's between n minus 1 into p minus delta c log n and n minus 1 into p times plus delta c log n. All right. But again, the point to recall is that the di's are not independent. Right?
You see 1 minus 2 into
Which one?
the above.
The above property is
1 minus 2n power.
why?
The down one which we took.
Okay, as I said, the di's are not independent. Right? So I can't say that this is equal to product. If they were all independent, then this would just be equal to product over all I, probability that whatever di minus n minus 1 times p is less than delta c log n. Right?
So
If they're independent.
second one is we need to compute the probability for I equal to 1 equal to 10.
Okay, I could try to do that. But again, I have to take care of the joint distribution, right? So I have to be careful because this is not true. It is not equal to the product of these probabilities. Which one? So this one depends on all the random variables d1, d2, d3 up to dn.
And what about the below?
That also depends on d1, d2, d3 up to dn. Okay. Okay, so any suggestions on how we can, after all we are interested in is getting a bound on this particular quantity. Yeah. Equal to, why? Okay, and what are you using? Okay, so maybe to help, let me write this more formally. Right? That's where formalism helps. This is equal to, so if I consider each of these, if I look at this particular event, right? So this is some event, let me call it AI.
Basically, intersecting circle. Like I'm giving it in terms of sets.
Okay, so again, very carefully, this is some event that depends on all of the AIs, right? How can I describe this big event in terms of the individual events? What kind of an operation am I performing?
Union.
It's a union, right? So I want to find what is the probability that at least one of the AIs occur, right? And that is simply a union of events. At least one of these occur. So this is equal to simply union I equal to 1 to n AI. And how can you bound the probability of the union of events in terms of the individual events? Summation, right? Just by the union bound. This is less than or equal to summation I equal to 1 to n probability of AI. So this is, in fact, basically comes from, well, one way to look at it is set theory, of course, but also the definition of probability, right? You know, the probability of two disjoint events is equal to the sum of the probabilities of the events, and if they are not disjoint, then basically you're overcounting, right? The probability of the union is just union of these two, and when you take probability of this event plus the probability of this particular event, you are overcounting the intersection once. Okay, so now we know we have an upper bound on the probability of AI, right? What is it? This is 2 times n to the minus delta square c by 3. Right? So this is just, again, this is the same for all I. So I just incur another n. So this is 2n e to the minus delta square c divided by 3. And this quantity tends to 0 as n tends to infinity, as long as n to the power. As long as delta square c divided by 3 is strictly larger than 1, because I also have an n here. Right? So this is just 2 times n to the power 1 minus delta square c divided by 3. Right? So as long as delta square c by 3 is even just a little larger than 1, this is fine. Okay. So this is a trick that you keep using. So in general, when you have a bunch of dependent random variables or dependent events, you try to bound each, try to get some kind of an exponential or at least a polynomially decaying probability bound for each of those events. And as long as the bound is less than the number of events themselves, you can just use the union bound to show that this is vanishing. All right. Any questions? Okay, so I think this is a good time to stop. So just a quick reminder, you have the homework 1 which has been uploaded. So please try to solve that because we'll be using many of those things in class. For example, what is a moment generating function for different random variables and so on. All right. Okay, so let's stop here.